Let's put together a couple of things we know now. We know that when a wire has a current running through it and it's in a magnetic field, that the wire experiences some force due to that magnetic field. It has moving charges, and moving charges experience a force through a magnetic field. We also know that a wire that has a current running through it creates a magnetic field. So, if we have two wires next to each other, we can look at the magnetic field created by one at the location of the other and note that there must be some kind of a force between those two wires as a result of each of them having current running through them. So let's examine that for this situation. We'll do each of these separately, but we'll start with the force acting on I2 caused by the magnetic field that I1 is generating. So first let's think about the direction of the magnetic field that I1 is generating. So point your thumb in the direction of I1 and wrap your fingers around to the location of the second wire here, and we'll see that your fingers would have to point into the screen here. So that magnetic field is pointing into the screen. Now, if you wanted to find the direction of the force caused by that magnetic field, we do V cross B to figure out the direction of F. So V is the direction of the charge movement, so that's up and this way. That's the direction that your pointer finger goes in. Your middle finger goes in the direction of B, which is into the screen, so you should be pointing your middle finger up toward the top of the screen. Your pointer finger is up toward the top of the screen. Your middle finger is pointing into the screen, and you'll end up with your thumb pointing to the right. And so there's going to be a force to the right. The force by 1 on 2 is going to the right. I keep saying right, but it's to the left there. Now we could do the same thing for the other current here. So if we look at the current for I2, put your thumb in the direction of I2, so your thumb should be pointing upward. And your fingers are going to wrap around at the location of I1. Your fingers would have to kind of be behind the screen here. They'd be coming out towards you. So at this location, we have a magnetic field from the red wire that's out of the screen. And again, if we look at the cross product here between the velocity of these charges and the magnetic field, we do the cross product so that our pointer finger is going to point upward. Your middle finger needs to point out of the screen in the direction of the magnetic field, and you'll see that your thumb then has to point to the right. So we get this force to the right. The force by 2 on 1 goes to the right, which makes sense given what we know about Newton's third law. These two wires are acting on each other. They should act with the same amount of force and in opposite directions. Now let's figure out how much force that is, and we'll verify that those two forces are equal to each other as well. So 2 steps in these problems. If we want to figure out the force on I2, we need to figure out the magnetic field at that location caused by the blue wire, and then we need to use that magnetic field to calculate the amount of force on this wire. So let's see, for I2, I guess I'll go back to red here. Whoops. There we go. Actually, I guess the magnetic field is created by I1, so we use blue. So the magnetic field at that location, magnetic field in general, for a current carrying wire is mu naught over 2 pi times I over R. So here, the magnetic field caused by 1 at this location, at the spot where the wire is, that's going to be mu naught, which is our 4 pi times 10 to the negative 7th, and that is Tesla meters per amp divided by 2 pi times the current, that's the current of this wire, because we're looking at the magnetic field created by this wire. So that's I1, that's 1.0 amps, divided by the distance from this wire to this location where we're looking at the magnetic field, which is 0.20 meters. So the magnetic field then, at that location, and these will cancel, leave us just with 2 there. 2 times 1 divided by 0.2 would be 10 times 10 to the negative 7th, so that's 10 to the negative 6th Teslas, and that is into the page. And then the force caused by 1 acting on wire 2, that's always equal to the magnetic field. So that's magnetic field 1 for the blue magnetic field here, times the current, and that'll be the current on this wire, so current 2, times the length, and it's the same for both of those, times sine of the angle. And that's the angle between the magnetic field and the current here. So the force from 1 on 2 is going to be equal to 10 to the negative 6 Teslas times, what did we say I2 was? 2 amps, times the length of the wire is 0.3 meters, times sine of 90 degrees. The current is up and the magnetic field is into the page. That's a right angle between those. So the force from 1 acting on 2 is, that'd be 0.6 times 10 to the negative 6th, or 6 times 10 to the negative 7th newtons. Now, if we go the other direction, we'll find very similar calculations, just rearranged a little bit here. So let's do that now. We'll figure out the force acting on this first wire that's caused by the second wire. So first we need to figure out, alright, what's the magnetic field at this location caused by this wire? So magnetic field is that mu naught, so that's 4 pi, there we go, times 10 to the negative 7th Tesla meters per amp over 2 pi times the current, and it's the current from this wire, because that's the one creating the magnetic field, so that's 2.0 amps, divided by the distance, 0.20 meters. And so we'll have this cancel, it gives us just 2. 2 divided by 0.2 is 10, so this is 20 times 10 to the negative 7th, or 2 times 10 to the negative 6th Teslas at that location, at this spot right here. And then our magnetic field is going to cause a force on the force caused by wire 2 acting on wire 1 here, which is going to be equal to the magnetic field, that's the one caused by the second wire, times the current in the first wire, times the length, times the sine of the angle between those. So the force from 2 on 1 is 2 times 10 to the negative 6 Tesla, times the current for the first one, which was 1.0 amps, times the length, 0.3 meters, times sine of 90 degrees, and so the force from 2 on 1 ends up being, that's 6 times 10 to the negative 7th newtons. And this one is to the right, and this one is to the left. So those forces are equal in size and opposite in direction, just as we would have predicted from Newton's third law, but we can verify that with these calculations.